On September 1st, 2022, a team of 16 scientists published a paper that shook the foundations of what we know about the universe. They observed distant galaxies with the James Webb Space Telescope and discovered something utterly surprising. The common understanding was that the universe underwent rapid expansion before cooling down. Then, the first stars and galaxies started to form during a time we called the Dark Ages. But here's where scientists started scratching their heads. These ancient galaxies appear to be as developed as our own Milky Way, and in some cases, even more mature than astronomers had anticipated, which raises one of several possibilities, that they may have existed way before our galaxy. Now, why is that a big deal? Apparently, this finding of ancient galaxies is going to challenge our understanding of how the universe began.
There is a Big Bang, but the Big Bang was not the beginning. People tend to think that if you have a model in which it keeps on going in some sense, and your Big Bang is not the beginning, that you've got to collapse back.
So a fundamental question arises. Is it time to reconsider what we think we know about the Big Bang and the origin of time? Before the early 1900s, most scientists thought the universe was static and unchanging. It means no expansion, no contraction, or any other changes taking place. But all that changed about a century ago. Astronomer Vesto Slipher noticed some nebulae were moving away rapidly. He first thought it was because of our galaxy's motion, but more observations from the Lowell Observatory in Arizona didn't support this idea. That's when Edwin Hubble stepped in. He showed a clear pattern that the further away a nebula was, the faster it moved away from us. And what's more interesting is that these discoveries matched what general relativity predicted, that space-time could stretch or shrink. And so, if we trace back the universe's expansion using Einstein's equations, we land on the idea that all space, mass, and energy were once squeezed into a tiny point, a singularity. We often hear the universe began with this singularity, followed by the explosive Big Bang. If we think about it, the scale of the universe is mind-boggling, and the events just before the Big Bang are still a mystery. Now, if everything started from that point, what existed before it? Was there really nothing, no space or time, before the singularity? In order to understand how the rewinding time went back to billions of years ago, let's consider this scenario. Think of our universe like the surface of any balloon. Here we have to introduce the concept of scale factor. The scale factor is like the ruler to measure the balloon's size. Right now, our universe is blown up to a certain size, which we call one scale factor. But some time ago, this balloon was only half as big. 2 dots will be drawn on this balloon, so if we blow it up, the dots move farther apart, and that's the expansion we mean. So in some future moments, the scale factor for this balloon will be larger than 1. Now think about letting the air out of the balloon slowly. As you do, everything on the surface comes closer together. If you could completely deflate the balloon, you'd have a tiny, flat piece of rubber. This is a bit like the singularity, when the whole universe was very close together, extremely hot and super dense.
If you extrapolate those equations back in time and try to predict what the conditions were at earlier times, you come to a moment 14 billion years ago when the temperature and density become infinite.
But just when you feel you've grasped this bizarre notion, it turns out the picture might not be so clear. Currently, there's strong evidence suggesting we shouldn't take Einstein's equations all the way back to a singularity. For instance, observations hint at a time just before 10 to the negative 32 seconds, when the universe underwent a super-fast expansion, known as cosmic inflation. Cosmic inflation offers valuable insights into the universe's expansion at a vast scale. It tells us why the universe looks so consistent and how galaxies came to be. In a way, it solves several puzzles in the Big Bang theory. But still, the singularity is a condition of intense density on a minuscule scale, where quantum forces play a vital role. So just using general relativity alone, we can't fully grasp the phenomenon of singularity. This early rapid expansion helps iron out issues with the Big Bang theory. We might need to rethink this whole Big Bang singularity concept, since it will probably reshape our understanding of cosmic inflation and the beginning of the universe. So, what truly unfolded at the start? It turns out that the peculiar nature of the Big Bang singularity suggests it might not be the whole picture. Mathematical singularities in a physical concept usually raise some eyebrows. They often mean the theory has gaps or has been pushed to its limits. And that's where we stand now. We've rewound the universe using general relativity, but this theory isn't all-encompassing. At the extreme densities and temperatures of the Big Bang singularity, general relativity clashes with quantum mechanics.
We're not really sure scientifically that there was a beginning to space and time. In fact, we've been exploring the idea that when you actually replace Einstein's theory with an improved theory of gravity, that you'll find that the Big Bang was not the beginning, that there existed space and time beforehand, and in fact, the key events that created the large-scale structure of the universe and even all the galaxies and stars, all those events actually occurred before the Bang. And we only exist here because of those events.
Professor Roger Penrose provided us with a new framework of thinking. He asked us to imagine what or who's in this universe if we fast forward time to infinity.
Who's in this universe eventually? Not us. The black holes will all have evaporated away by Hawking evaporation. They've swallowed galactic clusters. What's left in the universe? Pretty well photons. That the photons reach infinity without realizing anything funny has happened, if you put it like that. Infinity in this conformal picture is just like anywhere else.
So let's imagine that matter in the whole universe will eventually be dominated by photons. As you might have realized from relativity, the trouble with photons is that they don't feel the passage of time. Let's break it down. Think of a space-time like a grid in the fabric of the cosmos. We can measure separation on this grid using the space-time interval equation. Here the term tau is the time we feel, and the term ds squared is a variable to measure the space-time gap, or separation. For us who are stationary, our movement on this grid is all about time and not really about space. I mean, we're still traveling through time. So the equation now becomes this. It tells us that the separation the object travels in this combined space-time world is just based on time. This time distance relates to the speed of light and a special kind of time interval. Now, if we had something that could teleport, let's say in the x direction, its motion would be all about space. So we're left with this equation, which means two events in the space-time grid that happen at the same time, but at different positions in space. But photons are truly unique. They travel along a specific path known as null geodesics. What's fascinating is that photons move in such a manner that they don't experience time or space. They're instantaneous. This is why their space-time interval becomes ds squared equals 0. So let's imagine this. You turn on a flashlight briefly and then turn it off. The instant the light shoots out is event A, and the moment it reaches a certain point away from the flashlight is event B. The space-time separation between these two moments is ds squared equals 0. That's because the photon moves from A to B simultaneously, cruising through both time and space in a way that they offset each other. This unique way of moving means that photons lack a rest frame. They don't possess a personal clock as the rest of us do, so they never feel time passing by. This special behavior matches up with a fundamental idea in physics, that no matter where you are or how you're moving, light always moves at a consistent speed. If photons had a stationary reference point, it would appear as if light isn't moving from their view. This very fact contradicts our understanding of the speed of light. Also, the equations governing light are the wonderful equations due to James Clerk Maxwell, aka the Maxwell equations. These have a very interesting property. It lies on the fact that the equation couldn't tell big from small. The vastness of the universe, or the smallest quantum particles, they're all the same if we use these equations. For instance, if you have a system in which you've got some electromagnetic field, and you could stretch this system to bigger or smaller, it doesn't notice the difference. This phenomenon is called conformally invariant.
If you don't mind stretching or squashing, then you could step outside this universe to another side to it. So I want you to imagine the same thing here, that you've got the Big Bang, which is somehow stretched out to be a one-time surface, but you could go before it. This mathematical trick, if you phrase condition on your universe in this way, you say you could extend to before, then that is a way of characterizing the initial state of the universe.
As Penrose explained it, if we put the concept of an infinite universe in this conformal picture, every conceivable space is just like anywhere else, because essentially it's only mass that knows the difference. So although massless things might perceive all spaces the same, they lack the ability to mark time. This is when Einstein's theory helps us track when the universe started. Einstein told us that energy and mass are basically two sides of the same coin. But another important equation came from Max Planck, who said that energy and frequency are linked. E equals hf. If we put these two equations together, we realize that mass and frequency are connected. This means anything with mass like a rock or an apple has its own beat or rhythm. And so without mass, we wouldn't have a clock or time. In the end, Penrose's argument eventually leads us to this, that the very remote future is indistinguishable from a Big Bang. When the universe has become basically empty, except for photons, it would be as though it had transitioned into a new Big Bang phase. Our universe's future could become another universe's beginning. This concept, often referred to as conformal cyclic cosmology, challenges conventional ideas about the beginning and end of our universe.
Supernova exploding stars showed that the universe is actually undergoing this exponential expansion. It seems to be a feature of this term that Einstein introduced into his cosmology for the wrong reason.
So our understanding shifted yet again. We've come a long way to the idea that maybe something existed before the Big Bang. It wasn't just about how the universe started anymore. It was about whether it might have always been around. Our ancestors looked up at the night sky and saw a constant, a universe that was eternal and unchanging. They conceived ideas of cycles of creations and destructions that reset the cosmic clock. Even Einstein initially believed that the universe was static, but in his own mathematical equations from the theory of general relativity, it suggested that the cosmos might actually be expanding, which is not something he was hoping for. He introduced something known as the cosmological constant, symbolized as lambda. Einstein considered this as the biggest blunder of his career, since the lambda value isn't equal to 0. Fast forward to today, we know that even his biggest blunder was in fact correct in predicting an expanding universe, thanks to the groundbreaking discovery made by Edwin Hubble.
The current view is that the universe began with what's called the Big Bang. Immediately following that was a stage of inflation, which was an exponential expansion.
What we see is that this pattern of exponential expansion is expected to continue indefinitely. And so, turning the clock back to the universe's inception right after the Big Bang, cosmologists have uncovered evidence of a similar explosive expansion. Particle physicist by the name of Gabrielle Veneziano proposed an intriguing idea. What if the inflationary phase didn't occur after the Big Bang, but before it? In his short paper entitled Introduction to Pre-Big Bang Cosmology, he postulated that at some remote time much before the Big Bang, the universe was not particularly homogeneous, and that the inflation was natural, thanks to the duality symmetries of string cosmology. This idea is a game changer. It opens up a new start to how we see the universe's narrative, extending far beyond the initial cosmic event. Now, if we tie it back to the cyclic cosmology, Roger Penrose had a bit of a different take on this.
The view I'm taking is that what we regard as the current picture of the universe, but without inflation, expansion and then the accelerated expansion, is just one eon, which is one of a succession of such eons.
So what exactly is an eon, according to Penrose's viewpoint of the inflation theory? Let's break this down further. In the concept of conformal cyclic cosmology model, Penrose envisions the cosmos not as a one-time singular event, but as a series of epochs, each referred to as an eon. Yes, you heard that right. According to this, our universe is just one chapter in an endless cosmic cycle. So in this concept, our current eon began with the Big Bang. In this case, there's no need for the inflation theory in the traditional sense. Instead, the universe simply expanded from the Big Bang. eventually entering a phase of exponential expansion that goes on forever. And that's what Penrose defines as one eon. But here's where it gets more mind-bending. Penrose proposes that before our eon, there was another one, and the exponential expansion in that remote future of the previous eon appears to us as the inflation at the start of our eon, not after the Big Bang, but a prelude to our Big Bang. This really flips the script on traditional concepts. It suggests that what we perceive as the aftermath of the Big Bang could actually be the remnants of a universe that existed before ours.
Our Big Bang was the result of the remote future of an eon prior to ours. Now that's a crazy idea, but this idea is crazy, and often we find that ideas seem crazy turn out actually to be right. So the hope here is that this crazy idea does turn out to be right.
So what's particularly crazy about this idea? It's the notion that each eon begins hot and densely packed, expands, cools, and then enters a phase of exponential expansion, eventually becoming extremely cold. This cycle happens over a duration that is almost impossible for the human mind to grasp. You see, this will happen in time frames spanning Google years. That's 1 followed by 100 zeros. At this point, it's just like trying to imagine infinity. In Penrose's CCC model, he suggests that each cycle of an eon, from start to finish and then starting over again, lasts for a Google years. Then, after another Google years, another one will come about, so on and so forth. And in such a vast expanse of time, the main actors will be only the photons, the particles of light.
And what do photons do? They don't get bored because photons get right out to infinity without experience any time. Infinity is just like another place. So it means that the remote future of our expanding universe becomes the Big Bang of the next eon. And our Big Bang was the result of the remote future of an eon prior to ours.
How does all of this crazy idea stack up to today's topic? This accelerated expansion interestingly hints at a cycle much grander than we previously imagined. It suggests that the far future of our universe, in its endlessly expanding state, might physically resemble the conditions of another Big Bang. And so, the so-called Our Big Bang could be seen as the continuation of a previous eon that had also expanded exponentially. Quoting Roger's word from his 2005 paper on the CCC model, he stated that the conformal infinity of each eon joins conformally smoothly to the conformally expanded Big Bang origin of the subsequent eon.
Why was that structure there? Well, if there was nothing before it, it's hard to answer that question. Here we say, yes, it had that structure at that Big Bang because the eon before had the structure it had. Of course, it's an endless chain which goes on forever, but nevertheless, you can sort of, at each stage, answer that question.
The narrative presented by CCC naturally prompts us to contemplate the consequence of a cyclical cosmos. Within this framework, Penrose introduces another intriguing element of the cosmic puzzle, dark matter. Composed of hypothetical particles, Penrose coined the term erebons to describe them. This term draws inspiration from the Greek mythology figure Erebus. Erebus was the god of darkness, symbolizing deep darkness or shadow. It personifies the impenetrable darkness before the universe's creation, which is parallel to the mysterious nature of these erebons, the theoretical particles. In Penrose's argument, these hypothetical particles could explain dark matter's gravitational effects without invoking other forms of unknown matter or energy. Their gradual decay and the release of energy in the form of gravitational waves could significantly influence the universe's structure, especially at the end of an eon. This decay process is pivotal for CCC's explanation of the universe's low entropy state at the Big Bang. You see, the transition from a highly entropic universe, replete with black holes and remnants of past eons, to a low entropy state required for the Big Bang to start a new eon. All of this could be mediated by the actions of erebons. Overall, this mechanism would ensure that each new eon starts from a state of low entropy, which sets the stage for the universe's formation of galaxies, stars, and planets as we know them.
So this is the key part of the argument. The squashing and stretching is physically sensible. And many of my colleagues in cosmology, I may say, have a lot of trouble swallowing it. And I'm hoping, since you're not, most of you cosmologists, you probably have an easier time to swallow it than they do.
CCC suggests that the low entropy of the Big Bang wasn't randomly selected, but was instead forced into a low state by conformal transformations, removing the gravitational degrees of freedom of the previous eon. In order to demonstrate how unlikely it was that the entropy was chosen at random, Roger Penrose, in his book, The Emperor's New Mind, stated that this now tells how precise the Creator's aim must have been, namely to an accuracy of 1 part in 10 to the 10th to the 120th power. But then he makes it clear by separating the idea from any kind of religious connection. He said in an interview, "I don't think that helps much. A being in the sense of a conscious being, something that the word God has applied to, is not the view which I hold to. I like to draw these pictures, and I'm amused when people pick it up and try to say, I'm claiming that there's a creator out there. That's not my view at all. Doesn't that sound more like an intriguing paradox?" On one hand, he describes the universe's initial conditions with precisions that suggest a creator's aim, which then highlighted the astronomical improbability of such precisions arising by chance. But on the other hand, he stopped short of attributing these conditions to an intelligent originator. And if you recall, Penrose also employs theological terminology in the Ereban's particle story. Yet at the same time, he maintains a purely scientific stance on cosmic origins. Here lies a juxtaposition that seems almost contradictory. How could a scientist choose one over the other? Physicist Paul Steinhardt argues that the cyclic model is fundamentally flawed. He contends that the issue lies in focusing on the scale factor when we should instead be concentrating on the Hubble radius.
If you're thinking about a cyclic model, it was conceptually wrong in the first place. It's conceptually wrong because the picture focus has you turn your focus to the scale factor. And what I want to argue is that you really want to have your focus on the Hubble radius. Because if you talk about what makes a universe cyclic, what you mean is that from cycle to cycle, the universe should look the same.
If we're looking at the CCC model, the Hubble parameter shows how quickly the universe expands. Initially, the universe was a super tiny ball, just 10 to the minus 25 centimeters. And this ball bounced very high, powered by a whopping energy of 10 to the 15th GeV. As it rises, the speed eventually slows down, and so does the universe's expansion. When it descends, the Hubble parameter drops back, and the universe shrinks back to 10 to the minus 25 centimeters. But just like throwing a ball into a trampoline, the moment right before the ball lands, there's going to be a push. This is our universe's dark energy, and in our case, it causes a contraction. The nudge from the dark energy makes the universe keep expanding again and again in a continuous cycle. This phenomenon mirrors the conformal cosmic cosmology model, which says that the universe keeps expanding and contracting in a cycle.
And more generally, what we're trying to do is make a theory which is complete and tight, where the past, the present, the future are all interlocked.
To get a feel for this, you have to think about the seemingly simple concept of now. In our day-to-day lives, we experience time as a continuous flow, but it can also be useful to think of time as a sequence of moments or snapshots. Everything that happens can be thought of as the unfolding of moment after moment and after moment. Now picture these moments lined up. Every earthly moment, every orbit around the sun, and every event in the entire universe. This would capture every occurrence that has ever happened or will ever happen. Every place in space and each point in time, from the start of our Big Bang to star formations in the Milky Way, to the birth of planet Earth about 4.5 billion years ago, even to big events last summer. Happening simultaneously, but in different places, define our sense of now. You can picture them on a single slice of space-time. Let's call it a now slice. We'd like to think we all agree on what's happening right now, moment by moment. But Einstein showed that strangely, when you take motion into account, this common sense picture of time goes out the window. If you think about the region of space-time from this cyclic cosmology model, we realize that there are different ways to cut this region to represent the individual now slices. And from special relativity, we know that someone who is moving will have a different conception of what's happening right now. And so the way they'll intersect this region of space-time will be at a different angle. It won't be parallel to our version of slices. Picture an entity in a galaxy 10 billion light years from Earth. And way over here, we have a person reading a newspaper. If the two are sitting still, their clocks tick off time at the same rate. And so, they slice the same now sheet. But now see what happens when this entity moves away from Earth. The entity's now slice cuts through the region differently. It means that the entity's present moment on Earth skips back a millennium, to times when Vikings sailed the seas, or when the Great Pyramid of Giza was built. If this entity moves toward Earth, its now slice leans into Earth's future by about a few thousand years. It might glimpse events like humanity reaching a Type 2 civilization level, or perhaps colonizing another galaxy. Anyhow, this concept of time slicing is especially important when we consider again the case with photons. There now includes the past, present, and future simultaneously. Just as we believe that all space exists, so does all of time. Everything that has ever happened or will happen, it all exists, somewhere and sometime. From Andy Warhol introducing pop arts to the world, to the end of the Cold War, from our first time riding a bike, to events that are yet to happen on other planets. It all fits into the fabric of space and time. And so, this idea is just like what Einstein mentioned some decades back, that the distinction between past, present, and future is only an illusion, no matter how persistent they might look.
Is time universal? In other words, is there an audible tick-tock throughout the galaxy? A master clock, so to speak? The answer, my friends, is no. Time is not absolute.
So let's recap where we stand now. According to Professor Penrose, our understanding of the universe's end may be far from complete. He proposes that in the distant future, another Big Bang could occur. He argues that this isn't a one-time event, but rather an optical illusion of sorts. The universe might go on forever, not in a repeating cycle of Big Bangs and Big Crunches, but in a continuous, unending sequence. He even boldly claims that this is the evidence of a previous universe, existing just before ours. And he said that with great certainty.
The evidence for it is really quite strong. The strength of the signal we see is a 99.98% confidence level, which is pretty strong. A single black hole gradually swallows most of the cluster. All that energy bursts through onto the other side.
So, what specific evidence was he referring to? To address this, we need to review the relevant context. Back in 2019, Roger Penrose co-authored a research paper published in the Royal Astronomical Society titled Apparent Evidence of Hawking Points in the CMB Sky. In this paper, he and his team claimed to have found several anomalies, potential evidence of a universe that existed before our own. As stated in their research, each anomalous spot would have originated from a highly energetic point-like source, resulting from the Hawking radiation of supermassive black holes in a cosmic eon prior to our own. Simply put, these dark spots may represent actual evidence of a previous universe, or, as Penrose describes it, an eon rather than a universe. It's important to note that the lifespan of each eon could stretch up to a Google years. And if time truly extends infinitely, the idea is that another Big Bang would eventually occur. What remains in this remote future is the ultimate fate of black holes. Penrose suggests that some of these supermassive black holes from a previous universe might become bound to the conformally stretched Big Bang of the next eon. The observed anomalies are proposed as evidence of this connection. Here we have to make it very clear that these claims are highly controversial and not widely accepted within the cosmology community. But let's take a step back for a bit. How does one argue that these spots are definitive evidence of black holes from a prior universe? Well, it all circles back to a concept long proposed by the late Stephen Hawking, known as Hawking radiation. The whole point is pretty straightforward. We are able to observe dead black holes left behind by earlier eons. These black holes, possibly as massive as 10 to the 14 times the mass of our Sun, would have evaporated through Hawking radiation. And so, in the grandest picture of this concept, these remnants would form what is referred to as a Hawking point. The so-called warm points, which are all about 8 times larger than the diameter of the Moon. As Penrose stated in his paper, we must bear in mind that despite Hawking radiation being of an absurdly tiny temperature, over the eon's history, the entire mass energy of the whole will be finally radiated away, and, in the conformal picture, this will take place within what would effectively be a single Hawking point H. Since we know that the Hawking evaporation of a supermassive black hole would generally take much longer than the current age of our universe, some information from a previous eon may seep into the next cycle. If you're interested in the full details, we recommend reading the paper yourself. There's a link in the description below. But without delving into the nitty-gritty details of what he mentioned in the paper, he and his team identified several characteristics of these Hawking points as anomalies in the CMB map. Now, for the moment you've all been waiting for, where exactly is this evidence on the map? These are their galactic coordinates. And if we map these visually, here is where they appear.
According to the equations, what you find is that these signals should influence the dark matter in the next eon, and you should be able to see signals.
Penrose reiterates his belief in what he humorously calls a crazy theory of mine. He suggests that our universe will continue to expand until all matter decays, and then a new Big Bang will occur. But occasionally, remnants from a previous eon may seep into our current one. But does this theory fully explain our universe? The biggest difference in predictions between CCC and inflation theory lies in what we should expect to see. CCC suggests that we would find imprints of a universe before the Big Bang, visible in both the large-scale structure of our universe and in the CMB. On the other hand, inflation theory requires that any point where inflation ends and a hot Big Bang begins must be causally disconnected from other regions. To put it simply, each region of the universe should not show any interaction with another, the past, present, or future. Our universe's properties should be independent of any preceding universe. Observations from missions like COBE, WMAP, and more recently Planck have put very tight constraints on the existence of such structures. We see no evidence repeating patterns, concentric circles, or Hawking points in the universe. When the data is analyzed properly, the findings consistently support inflation and not CCC. Although Penrose has his supporters, the scientific consensus strongly disagrees with his conclusions. Many scientists have pointed out that his predictions are not supported by the data, and any claims of finding such effects seem to rely on what they argue is a flawed or unsound interpretation of the data. Despite that, Penrose continues to advocate for this CCC idea.
When I'd had these various ideas, I could go on lecturing about this forever because nobody will ever know whether it's right or not.
Focusing on a slightly different aspect, we arrive at a specific feature of the universe, the dark energy density. Professor Penrose suggests that for life to exist, the conditions had to be extraordinarily precise. According to him, an advanced being might have fine-tuned the dark energy density to allow life to emerge. If this density were significantly higher, the universe could have been torn apart. Or, if it's only slightly lower, the universe could collapse into a singularity, long before any form of life had the opportunity to develop. So to make this clearer, let's consider a simple thought experiment. Imagine you're playing a game where you have to pick the right card out of 100 to win a prize. Sounds tough, but still possible, right? Now think about if that game was a lot harder, like having to pick the right card out of 1 billion. That sounds impossible. Well, this game illustrates how Professor Penrose views the universe's precision. He suggests that the universe began with conditions so exact, it's like picking the right number out of an unimaginably large pool, quantified as 1 part in 10 to the 10th to the 123rd power. This part alone means that we need 123 zeros to write this, so this whole part will have 10 to the 123rd zeros. That's insanely small. It's like saying out of countless trials, The universe got that one in a gazillion chance right, to create life as we know it. If it hadn't, we wouldn't be here to talk about it. Now here's where it gets even more interesting. This connection between life and dark energy density is surprisingly strong. But, and it's a big but, just because we're here to observe this universe doesn't mean our existence was a guaranteed outcome. The chances of the universe having just the right amount of dark energy for life to exist are incredibly slim.
There has to be some sort of causal connection between the universes. If all those other universes are just causally disconnected from our own, then nothing that happens in those other universes affects anything that happens in this universe, including whatever events were responsible for setting up the fine-tuning in the first place.
When we talk about the precision of the conditions needed to create the universe, if we say 1 part in 10 to the 10th to the 123rd, it reflects the precision on the phase space volume. V over W equals this number. It was Roger's fancy way of saying the different possible states the universe could have taken at its inception. Well, this precision is so specific that even if you try to write it out in full by putting a 0 on each separate proton and on each separate neutron in the whole universe, you wouldn't come close to the total. Not even close.
That many zeros, I certainly couldn't get onto the page. I couldn't even fit them into the universe if I put 1 0 on every single proton within the observable universe. That's not nearly enough.
What's interesting is that while Penrose references theories by Stephen Hawking, Hawking himself had a different view. In his 2010 research paper, Hawking stated, "Our universe seems to be one of many, each with different laws." He believed in the hypothetical set of all universes, a perspective quite different from Penrose's cyclic cosmology. In his own words, our cosmic habitat, now the entire observable universe, is just one of many. Speaking of the multiverse and how it relates to CCC, as briefly mentioned earlier, each cycle of an eon lasts for about a Google years, a staggering number that is 1 followed by 100 zeros. So a Google years is 10 to the 100 years. Then there's the concept of a Googolplex, which is 10 raised to the power of a Google. Here we're going to delve into the consequences of a Googolplex universe. So let's recall the phase space volume we mentioned previously. It's a theoretical space that represents all possible states that the universe can exist in. This volume is an astonishing 10 to the 10 to the 123rd cubic meters. It's so vast it defies conventional understanding of scales. Our current observable universe, that is, the part we can see with our telescopes and instruments, is around 10 to the 26 cubic meters in volume. While this might seem unimaginably large, it is still minuscule compared to the theoretical size of the phase space volume, even a Googolplex universe we're talking about. Now, just for the sake of argument, let's imagine a universe that extends a Googolplex meters across. If you were to traverse such a vast universe, you'd eventually start to notice something peculiar: repetitions. And not just any repetitions. I mean repetitions of yourself, an exact copy of you. The reason behind this repetition lies in the concept of quantum states. To put it simply, a quantum state is a specific arrangement of particles and fields in a defined system. In the context of the human body, this means considering the unique arrangement of its atoms and particles, everything that makes us who we are. The total number of quantum states that describe the space we occupy is around 10 to the 10 to the 70th, assuming that we're roughly occupying about a cubic meter of space. If you're wondering where this number comes from, it is derived from the combinatorial possibilities of arranging particles under maximum entropy of a system, taking into account the limits set by the Heisenberg uncertainty principle. For example, when considering entropy in black hole thermodynamics, it was found by Stephen Hawking and Jacob Bekenstein that its entropy is proportional to the surface area of its event horizon. However, when considering ordinary volumes of space, the number of quantum states depends on the volume and the types of forces within it. And so, for a volume of 1 cubic meter of space, there are a finite but extremely large number of possible configurations. So now let's put this into perspective. If you occupy a space of roughly 1 cubic meter, And there are about 10 to the 10 to the 70th possible quantum states for that space. This means there are this many different possible versions of you in terms of atomic arrangements. It could be the atomic arrangement of you resembling famous celebrities, your favorite animal, or a complete arrangement of you without any atoms at all. The thing is, you could be anything. But despite those gigantic possibilities of what you could have been, that number is still far less than a Googolplex. So the basic idea is that if you were to travel a Googolplex distance away from yourself in this hypothetical universe, you'd eventually encounter another arrangement of atoms that exactly matches yours, another version of yourself with the same exact brain chemistry, the same thinking process, and the same behavior. And so, in a sufficiently vast Googolplex universe, repetition is not just possible, it is inevitable. If we live in a universe as vast as a Googolplex across, where space stretches on forever, then not only could there be another you out there, but there could also be endless variations of you and everything else. Perhaps you will be marrying your biggest crush. I mean, every possible arrangement of particles, every possible history, and every possible future would exist somewhere in this vast multiverse. Based on our current understanding of the universe, if we turn back the clock far enough, we encounter conditions of extreme density, temperature, and energy. Under these conditions, we approach what is known as, you guessed it, a singularity. If the distance scales become too small, time scales too short, or energy levels too high, our current understanding of physics breaks down entirely. Now consider reversing the clock back approximately 13.8 billion years, right up to the hypothetical zero mark of the Big Bang. This point is known as the Planck era, exactly 10 to the minus 43 seconds after the Big Bang. This period from the Big Bang to the end of the Planck time is referred to as the Planck epoch, a realm beyond the reach of our current physics. So to grasp how incredibly short the Planck time is, let's imagine how many Planck times fit into just 1 second. Let's think of this in two ways. First, consider that the universe is nearly 14 billion years old. If we use this age as a single unit of time, a universe, then there are more Planck times in 1 second than there are seconds in 10 million trillion universes worth of time. Pretty mind-bending, right? Now let's look at it another way. Our galaxy, the Milky Way, contains roughly 100 billion stars. Then there are approximately 2 trillion galaxies in the observable universe, so each with about 100 billion stars. Now imagine that each star in the universe has 300 identical Earths orbiting it. I mean exactly identical Earth just like ours. So here's the mind-boggling part. If you counted every grain of sand on each of these planets, around every star, in every one of the 2 trillion galaxies, you would begin to approach the number of Planck times in a single second. 1 grain of sand equates just how much a Planck time is in a second. It's astonishingly small. The Planck time can be thought of as the frame rate of our universe, while the Planck length represents its pixel density. According to our best understanding, during the Planck era, all 4 fundamental forces of nature were unified into a single superforce. Gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force were one aspect of the same thing, much like how water can exist in different phases like ice, liquid, and gas. If this depiction of the universe is accurate, then we would expect a series of phase transitions to have occurred in the early universe. Initially, as the universe expanded, all possible particles and their corresponding antiparticles would have been created in great numbers. As it continued to cool, these particles would have annihilated each other, converting their mass into radiation. The process continued until approximately 308,000 years after the Big Bang, when the universe became cool enough for neutral and stable atoms to form without being immediately torn apart by high-energy photons.
The theory predicts that at very high energies, there should actually exist forms of matter which turn gravity on its head and cause gravity to behave repulsively instead of attractively. The inflationary theory is basically the hypothesis that this repulsive gravity was the bang of the Big Bang. It's what set the universe into this period of gigantic expansion.
About 55 years ago, this CMB radiation was first detected, which provided strong empirical evidence for the Big Bang theory. It went from being one of several possible models for the universe's origin to the leading and only one that fits the observational data. But still, the proponents of the steady-state model, such as Fred Hoyle, resisted this shift. Despite the accumulating evidence, they continued to propose increasingly far-fetched explanations, but over time, these contrarian views faded into obscurity as their claims were increasingly shown to be trivially incorrect, and eventually their research programs ended with their passing. Could we be witnessing a similar situation with Penrose's CCC? After all, finding patterns in the CMB data is something that requires thorough caution. The recent B-mode findings from the BICEP-2 experiment have sparked intense debate. This is a reminder that there is always a risk of interpreting patterns that are more reflective of our imaginations, the imagination of our algorithms, rather than genuine evidence. From the 1960s to the 2000s, cosmology developed at a quick pace with a strong focus on understanding the growth, evolution, and fate of the universe. There were observations that were no doubt true, but they also highlight areas where the Big Bang Theory lacks predictive power. The theory itself does a great job explaining a lot, but there are still phenomena in the universe that it does not account for. Some might say that each step in the formation of the universe could be chalked up to mere coincidence. But is it reasonable to attribute everything to chance, especially when considering the precision observed around us? Take, for example, the concept of intelligence, and that includes the overly rated artificial intelligence. Observations tell us that intelligence typically originates from an existing intelligence. So when we see the intricate design and order in the universe, it's natural to question whether it all could really be the result of random events. When we start to consider the sheer number of coincidences necessary for life to exist, this whole galactic time frame suddenly appears quite short. Can we truly believe that all these factors aligned perfectly by chance in what is, cosmologically speaking, a relatively brief period?
There is a transcendent creator beyond the universe who brought the physical universe into existence. And I think the scientific evidence is pointing in that direction fairly strongly, in part because we now have evidence, multiple lines of evidence, suggesting that the material universe does not look to have been eternal and self-existent.
To illustrate this further, imagine you're building a house. You gather all the materials, wood, nails, glass, and enlist scientists to explain every step of the construction process, from the physics of the structure to the chemistry of the materials. Even with a complete scientific explanation of how the house was built, it doesn't negate the fact that there was an architect behind its design. Understanding the scientific mechanisms that led to the formation of the universe and life within it doesn't eliminate the possibility of an underlying cause or intelligence. After all, what scientists are striving to achieve is to unravel the deepest mysteries of the universe. Physicist Richard Feynman once noted that discovering the laws of physics is like trying to learn the laws of chess, merely by observing chess games. You might observe that bishops remain on squares of the same color, deducing this as a fundamental rule. But a deeper understanding reveals that bishops actually move diagonally, which in turn explains why they always stay on the same color. This evolution of understanding, from a simple observation to a more profound insight, mirrors the journey of discovering physics. Discovering the concept of an expanding universe after Newton and Einstein wanting a static universe is a similar type of revelation. Another example is realizing that chess pieces maintain their identity. But consider a pawn reaches the opposite end of the board and finally transforms into a queen. Of course, it does not violate the laws of chess. You just had never seen a game pushed to that extreme before. So when faced with such mysteries that current theories can't explain, science generally offers two options. The first one is to devise new theoretical mechanisms to explain the phenomena. And secondly, to assume that the universe was simply born with the necessary properties for what we observe. As we all aware, only the first approach holds real scientific value. It is the path that scientists must take, even when it might not yield immediate results. After all, science is about following the evidence wherever it leads, and the universe itself will ultimately determine what is true and what is merely speculation.